In this lesson, we're going to talk about simplifying radicals and rational exponents. So before we get to simplifying radicals, let's identify the parts of a radical. So here we have the radical sign. This n that's over here, that is called your index. If it is a square root, the index would be 2, but it wouldn't be listed. So for instance, the square root of x, we don't put a little 2 here because it's understood that that is a 2. If you see any other number there, like a 3 or a 4 or a 5, that is telling us that the index is that number. The expression under the radical is called the radicand, and this m here is the exponent. So we're going to look at a couple of different types of roots, and the first one's going to be the square root. Square roots are what we're kind of used to seeing. That's where your index is going to be 2. So what we're going to do is break this into two different types, and we're going to say that our exponent can be even or can be odd. So let's focus on the even exponents first. So if we have the square root of x squared, that would simplify to be x. Square root of x to the fourth would be x squared. Square root of x to the sixth would be x to the third. Now, if you're not sure how to get this, we can think about writing it out and then circling our pairs. So if I have the square root of x squared, for instance, there's two x's inside, x times x. With the square root, because our index is a 2, we're looking for pairs of the same term. So here we want to have two x's, and when you have a pair of x's, that will come outside of the radical as 1x. If I have x to the fourth, x times x times x times x, again, we're looking for pairs of the same thing. So we have a pair of x's and another pair of x's. So from this pair of x's, an x comes out of the radical. From this pair of x's, another x comes out of the radical. And we multiply these together, x times x, to get x squared. Okay, same thing is going to go for x to the sixth. If I have an extra two x's inside, I'll have three pairs of 2. So I have x times x times x, which would be x cubed. Now we can do this, but if our exponent is a large number, we don't want to write x out that many times. So what we can do here is give it a rule and say, okay, if we have x to any even exponent, our answer, if we look at kind of what we did here for the exponent of our radicand was a 2, our exponent for our answer is a 1. The exponent in our radicand is a 4, our exponent answer is a 2, exponent in the radicand 6, 3. So how are we going from one exponent to the other? Basically what we're doing is we're taking that power and we're dividing it by 2. Right? The index is a 2, so we're dividing it by the index. So if I had something like x to the 50th power, that would be x to the 25th, because 50 divided by 2 is my index, would give me 25. Now, what if the exponents are odd? So first off, let's look at the square root of x. Now, the exponent on the x is a 1, and the index is a 2. When your exponent is less than your index, you can't do anything, so we just leave it alone as square root of x. If I have the square root of x cubed, we can think of this one of two ways. So we could write out x 3 times, in which case we're looking for pairs again. So we have a pair of x's here, which would come out of the radical as an x, and then we have this x that's left over, and that would stay in the radical. So x square root x. Another way you can think about this is breaking this into two different radicals. So since 3 is odd, we can break it into x squared and x. Because our exponents, we have 2 and 1. If we add them, we'll get 3. And now the square root of x squared, that follows the rule for even. So we can divide 2 by 2 to get x, and then we have square root x. So square root of x to the fifth, again, we can write 5 x's out and circle our pairs, or we can break this into x to the fourth and x. Square root of x to the fourth is going to be x squared, with a square root of x left over. So when we have an odd exponent, we're always going to have a square root of x that's left over in our answer. So let's try one more. Square root of x to the seventh. So that's going to end up being x to the third square root x. So kind of following this pattern here. So let's make a rule for that. So let's say the square root of x to any odd number is going to be x to that odd minus 1 divided by 2 square root x. So the odd minus 1 is just meaning that you're changing it to the closest even without going over, and then we're dividing it by 2, and we're following this even rule. So if I had the square root of x to the 25th, I would take my exponent of 25, I would subtract 1 to make it even, so 24, divide it by 2, so I'd get x to the 12th out of the radical, and then I'd have a square root of x left over. So if we look at a couple of examples, I'm going to break each of these down separately so that we can see how you kind of smush it together. So first we have a square root of a to the 8th. Now 8 is even, so we can divide 8 and 2, so we get a to the 4th. Then we have the square root of b to the 18th. 18 is even, so 18 divided by 2 is b to the 9th. These are both outside the radical, so we're just going to put them together, a to the 4th, b to the 9th. And that's going to be our simplified answer. For number 2, we have a number in front, so square root of 81, and that's just going to be 9. Then we have the square root of x to the 4th. That's even, so 4 divided by 2 is going to give us x squared. Okay, nothing else is left over, so we put these together, 9x squared. Okay, for number 3, we have the square root of 27. And since 27 is not a perfect square, we can think about breaking it down, right? So 27 can break into 9 times 3, and then 9 breaks into 3 and 3. We can't use the 27 or the 9, so we're looking for pairs. We have a pair of 3's here, so that's going to be a 3 on the outside, and then we have a 3 left over, so 3 on the inside. And next we have the square root of a, and since the exponent is less than the index, we're just going to keep it as square root of a. And then for square root of b cubed, it's odd, so we're going to subtract 1 to make it 2, divide it by 2 to get 1, square root b. So now we want to put it together, so anything on the outside will stay on the outside. So we have a 3 and a b. And then anything underneath the radical stays together, so 3ab. And that is our simplified answer. All right, so let's try one more here. We have the square root of 52. So let's break 52 down. I'll just do this up here. So 52 is going to be 2 and 26. And then 26 is 2 and 13. So can't use, can't use. So we have a pair of 2's. So 2 will come out of the radical. 13 stays in the radical. Next, we have the square root of x to the 5th. So that's odd. So you're going to make it square root, I'll just kind of write this out really quick. Square root of x to the 4th with a square root of x left over. We're going to use our even rule. So this will be x squared, square root x. Then we have the square root of y to the 4th, and that's even. So 4 divided by 2 would be y squared. And then lastly here we have the square root of z to the 6th. That's again even, so z to the 3rd. And now we're just going to take everything that's outside. So 2x squared y squared z cubed. 2x squared y squared z cubed. And then inside we have a 13 and an x. Okay, so next we have other roots besides square roots. So here we have cube roots with variables. So cube root means that the index is going to be a 3. And again, we're going to break this up into 2 different types of scenarios where we have multiples of 3 and then not multiples of 3. So let's look at some examples of this. So if I have the cubed root, now notice I'm making a little 3 as my index. I have to make sure I write that in. Cubed root of x cubed. That's going to be x. If I have the cubed root of x to the 6th, that's going to be x squared. Cubed root of x to the 9th is going to be x cubed. And again, we can kind of think of this a couple of ways. So if we're thinking it as drawing it out and trying to visualize it, x cubed, let's say this first one, is x times x times x. Well, we're looking for, based off of the index, we're looking for 3 of the same thing. So if we're looking for 3 of the same thing, here's 3 x's. So that's going to come out of the radical as an x. If I had x to the 6th, there's going to be 2 groups of 3. So that's how I have x squared, and then so on and so forth. So let's make a rule and say if you have the cubed root of x to any multiple of 3, it's going to be x to that multiple of 3 divided by 3. So what we're always doing, this is very similar to what we did in the square root scenario. You're taking that exponent and we're dividing it by our index. So if we take, for instance, an example of the cubed root of x to the 36th, this is going to be x to the 12th because we're dividing 36 and 3. Now what happens if it's not a multiple of 3? So cubed root of x squared. Okay, so here the exponent is less than the index, so we can't do anything, so we'll leave it like that. If we have the cubed root of x to the 5th, we can think of this 2 ways. So let's think of it visually first. So we have x to the 5th, so that means there's 5 x's multiplied together. If I'm taking the cubed root, I need 3 of the same. So 1, 2, 3 of the same. So that's going to come out of the radical as an x. And then in the radical, there's 2 x's that we didn't use. So that's going to be x squared on the inside. So visually, we can draw it out like that and circle it. We could also break it down and say, well, 5 is not divisible by 3. So what's the closest number divisible by 3 without going over 5? So we can break this into the cubed root of x to the 3rd times the cubed root of x squared. Because the exponents, 3 and 2, if I add them, I get 5. So the cubed root of x cubed is divisible, like 3 is divisible by 3, it's a multiple of 3. That becomes x. And then we have a cubed root of x squared left over. If I have the cubed root of x to the 7th, 7 is not divisible by 3, so the closest number would be 6, and that means that there's 1 left over, 1x. So the cubed root of x to the 6th, we're going to use the rule for multiples of 3. 6 divided by 3 is x squared, and then we have the cubed root of x left over. So if I had something like the cubed root of x to the 29th, 29 is not divisible by 3, so we're going to break it into x to the 27th and x squared. So 27 and 2 gives me 9. Cubed root of x to the 27th, we're going to divide 27 and 3, so we have x to the 9th cubed root of x squared. So if we look at a couple of examples of this, here we have the cubed root of 24a to the 11th. So we can see that there's a number first. Okay, so cubed root of 24. So we're going to break 24 down like we would with our trees. So anything that multiplies to 24, so I'm going to do 2 and 12, and then 12 I'm going to do 2 and 6, and then 6 I'm going to do 2 and 3. So can't use these numbers. So because we have a cube root, we're looking for groups of 3 of the same number. So 1, 2, 3. There's 3 of the same number right here. So that means that that 2 is going to come out of the radical, and that means that we have this 3 left over, and that's going to be inside the radical. Then we have the cubed root of a to the 11th. 11 is not divisible by 3, so we're going to make this cubed root of a to the 9th with cubed root of a squared left over. Divide 9 by 3, so this is going to be, oops, oh my gosh, excuse me, this is going to be a cubed here, and then cubed root of a squared. So now if we want to put this together, on the outside we have a 2, and we have an a cubed, and then on the inside we have a 3 and an a squared. Okay, now on this one here, we see that there's a negative under the radical. Now this is okay because the index is odd. So that means that you can have three of the same number and get a negative value when you multiply them, right? If you have three positives, you'll get a positive. If you have three negatives, you'll get a negative. When we have an even index, like a square root, if you have two positives, you get a positive. If you get two negatives, you get a positive. So there's no way to get a negative under the radical if the index is even. When that happens, we do have to pull out the I. But in this case, we don't, and that's fine. Our answer is just going to be a negative. So we have the cubed root of negative 64, which is going to be a negative number. And that's actually a perfect cube, 64, which is going to be negative 4. If you don't know that, just break it down. 64 is going to be 8 times 8. 8 is 4 and 2. So we're just going to break each of these up. And then 4 is 2 and 2 and 2 and 2. So when we think about what we have left, we want three of the same value. So here's 3 2's and another 3 2's. From each group of 2's, a 2 comes out, so we get a 4. All right, then we have the cubed root of f to the 6th. That's divisible, so that's going to be f squared. Then we have the cubed root of g to the 5th. 5 is not divisible by 3, so we're going to break this up and say cubed root of g to the 3rd and cubed root of g squared. Cubed root of g to the 3rd is g, cubed root of g squared. And then lastly, we have the cubed root of h squared. Because the exponent is less than the index, we can't do anything, so we'll leave it alone just like that. So now on the outside, we have a negative 4, we have an f squared, we have a g, and then on the inside, we have a g squared, and we have an h squared. Okay, and then we're just going to look really quickly at a couple of other types of roots. So we won't really see anything higher than a 5, but you can do this. These rules apply for any type of root that we have. So let's say we had the fourth root. If we had the fourth root of x to the 8th, 8 and 4 you can divide, so that's going to be x squared. If I had the fifth root of x to the 20th, 20 you can divide by 5, and that's going to be x to the 4th. If you have a number on the inside, so let's say we had the fourth root of 48, I'm just going to do this real quick. So 48, I'm just going to do 12 and 4, and then I'm going to do 6 and 2, and 3 and 2, and 2 and 2. So if you're doing something like this with numbers, the fourth root means that you need 4 of the same number. So, 1, 2, 3, 4. There's 4 2's, so we're going to get a 2. And then we have, not a 3, that's a 4. And then we have a 3 left over inside. So what we're doing is we're looking for 4 of the same number. If I had something like the fifth root of 1025 and I wanted to break that down, I would be looking for 5 of the same number. All right, and then when it's not multiples of the root, we're going to kind of follow what we did for the cubics. So if I have the fourth root of x to the 10th, 10 is not divisible by 4, so I'm going to break this into something that is divisible. So I'm going to break it into 8 and 2. So you always want to go to the closest multiple without going over. 8 divided by 4 is going to give me x squared, and then I have the fourth root of x squared left over. If I had the fifth root of x to the 24th, 24 is not divisible by 5, so I'm going to break it into x to the 20th and x to the 4th. So 20 divided by 5 would be x to the 4th, fifth root x to the 4th left over. So if we look at a couple of these examples real quick, we have the the fourth root of x to the 20th. 20 is divisible by 4, so we get x to the 5th. And then we have the fourth root of y to the 28th, and that's going to be y to the 7th. So we just smush that together, x to the 5th, y to the 7th. And then here we have the fifth root of 32, and that's going to end up being 2 because that's a perfect fifth root. And if you're not sure, you can write it down. That's going to be 16 and 2, 8 and 2, 4 and 2, 2 and 2. So I need, in this case, 5 of the same number since it's a fifth root. So 1, 2, 3, 4, 5. There are 5 2's and nothing left over. So a 2 comes out of that grouping. Then we have the fifth root of x to the 10th. 10 divided by 5 is going to give me x squared. And then we have the fifth root of y to the 16th. 16 is not divisible by 5, so we're going to break this into the fifth root of y to the 15th times the fifth root of y. And then 15 divided by 5 would be y cubed, fifth root of y. So now on the outside, we have a 2x squared y cubed. On the inside, we have a y. Right, and the last thing we're going to look at is rational exponents as roots. So you can rewrite a radical as a rational exponent. The exponent in the radicand is the numerator of our exponent, and the index of our radical is going to be the denominator. So for instance, if I have something like the square root of x, the exponent is a 1, the index is a 2. So this is the same thing as saying x to the 1/2. If we think about it the other way, let's say, let's say I have x to the 1/4. If I want to write it as a radical, the exponent would be 1, the index would be 4. This is very helpful because when we get through more in this chapter and going through just more in math in the future, being able to change from one form to the other is going to be helpful in helping you solve things where one way might be easier than the other. So k to the 2/3, if I want to write that as a radical, okay, 2 is going to be my exponent, 3 is going to be my index. I can't simplify this, so I'm just going to leave it alone. In number 2, I'm going to have the 81 inside. 3 is my exponent, 2 is my index. Now, since it's a 2, I'm not actually going to write it there since it's understood. And then I'm actually going to simplify this. So instead of doing 81 cubed and then taking the square root, I can take the square root first. So the square root of 81 is 9. And then I can raise it to the third power, which would be 729. And then for this last one, we have 32. The exponent is going to be a 3. The index is going to be a 5. We're going to take the fifth root of 32, which is 2, and then we're going to raise it to the third power, which is 8. So 32 to the 3/5 is just a fancy mathematical way of saying 8.